In today's class, we will try to learn about conductor, insulator and dielectrics from the electrostatics perspective. Okay. Uh, First is about the electrostatics of conductor. Let's try to learn some of the important properties of this conductor, rather electrostatic properties of conductors. Inside the conductor, both electric field and charge are zero. Inside the conductor, electric field as well as charges are zero. That means inside the conductor, no electric field, no charge inside the conductor. Okay. Number two, when a conductor is placed in an electric field, the electric field at any point inside the conductor is zero. That means when a conductor is subjected to an external electric field, then what happens? No electric field inside the conductor. That is the meaning. Okay, at any point inside the conductor, okay, electric field is zero. Now next, number three, equal and opposite charges develop on the surface of the two ends of the conductor. That means when that conductor is placed inside the electric field, equal and opposite poles, or rather charges, develop on the surface of the two ends of the conductor, and this will give you rather your electric field inside the conductor as zero, because due to that external field, what happen? Opposite field against the direction of the against the direction of the external field, equal in magnitude but opposite in direction, so they neutralize each other, and so electric field inside the electric field will be what? Zero, right? Next, number four, charge resides on the surface of the conductor. We know that charge only resides on the surface of the conductor, not inside. So what happens? Charge inside the conductor will be what? Zero. All points just below the surface of the conductor have same potential. As there is no electric field inside the conductor, what happens? At any point inside the conductor, electric potential will have the same value. Got it? Last point, since the charges are at rest on the surface of the conductor, therefore the electric line of force must leave the surface perpendicular at every point. So what happens? As the charges are at rest, not in motion, so there will not be no horizontal component parallel to the surface, and so what happens? Only what vertical component will exist there. That means perpendicular to the direction of the surface, perpendicular to the surface will be only there, and so what happens? No electric field exists parallel to the surface, and so what happens? Your electric line of force, or rather the direction of the electric field, will be leaving or entering the surface perpendicular to the surface at any point on it, right? Yes. Let's see about the insulator. In the case of insulator, what happens? There will not be no sufficient amount of free electrons are available, so what happens? No conduction of electricity is possible. In the case of dielectrics or dielectric material, okay, in such a dielectric material, what are these dielectric materials? Our purpose for the capacitance, okay, for having that capacitance with a dielectric medium, we need to know what is meant by dielectrics and what is meant by dielectric constant. Okay, you know, these dielectrics are nothing but these are insulators. Okay, these are insulators. What happened? Which type of insulators? Okay, not all insulators are dielectrics, right? There are some insulator which, when placed inside the electric field, okay, and which are able to produce what? Induced charges on its faces, are called dielectric. Okay, that means insulators which, when placed inside the electric field, if unable to produce opposite charges on the two ends of the insulator, then that type of insulator, when placed inside the electric field, unable to produce opposite charges at the two ends of the insulator, we call them as dielectrics. That is, these insulators, okay, when placed inside the electric field, produce polarization. That means the negative charges and the positive charges on the two ends of the insulator, we call it that phenomenon as polarization. So those insulators which when placed inside the electric field, okay, produces electric polarizations are called what? Dielectrics. We can also say that dielectrics are insulating material which transmit electric effects without actually conducting electricity. This is very beautiful and also important. Okay, without what? Conducting, what happened? The effect of electricity is transmitted from one point to the another point. So such type of insulator which has the property to what? Transmit electric effects without actually conducting it, we call it them as what? Dielectrics. Now how this dielectric medium, okay, are happening? If we look to that of the atomic level, then the atoms of this dielectric or conductor may be divided into non-polar atom and polar atom. Non-polar atom means what? Whenever there is no external field, if the center of the positive charge, rather inside the nucleus, okay, the center of the positive charge and the center of those electrons revolving around the nucleus, if they are centers, center of what and what? Center of positive charges and center of mass of the negative charges. I'm talking about center of mass, okay, center of mass of the positive charges and the center of mass of that of the electrons revolving around the nucleus. If they are residing at the same point, then that type of atom we call it as non-polar atom. In such case, what happen? Your electric field will be equal to 0, dipole moment will be also equal to 0. Now you know dipole moment is equal to what? Twice LQ, no? The length of the dipole times either of the magnitude of the charge, right? So either of the magnitude of the charge is there, as dipole length is 0, as their center of mass are residing at the same point, dipole moment will be also equal to 0. But in that case of polar atom, if there had been no electric field applied, also what happened? The center of mass of these two were positive charge and the negative charge, they will be separated, okay, little bit. That means they are separated. The center of mass of positive charge and the center of mass of the negative charge, they are separated slight distance, with a small separation of distance. Then what happened? That type of atom we will call it as what? Polar atom. Okay, not non-polar, it will be polar atom. That means two poles will be there. For example, like that of your water also, it is also a polar atom. Okay, rather you can call it not atom, rather molecule in that case, right? But we are talking about atoms, okay. But when such non-polar atom, if they are subjected to external field, if external field is applied, then what happen? You may think that on this side far away one positive charge is there, far away there one negative charge is there. So from positive charge to negative charge, electric field will be there. So you can take it or imagine that electric field is from left to right, okay. And that polar atom which was here, now what happened? Being positive charge heavy, nucleus is heavy, so what happened? This nucleus is practically immobile, okay. It will be somewhat there at its position, but all those electrons will be shifted, okay, in the direction opposite to that of electric field. So what happened? Electron will be moving toward the left side, right? So what happened? The center of mass of these electrons, okay, the center of mass of this electron will be there. The center of mass of the electron will be shifted toward the left side somewhere here, and that positive nucleus will be there as it is. So what happened? One center of mass of those electrons on this side, negative charge on one side, positive charge on one side, you can take it in that way. So two poles are formed. So we call it such type of atom as what? Polarized. That means two poles have been formed. Poles, no poles was there, but here pole has been formed. So we call it such atom as polarized atom due to what? Due to the external field. So such phenomenon takes place inside the dielectric medium when this dielectric medium is placed inside the electric field. Now to know this more about this polarization of this dielectric medium, let's try to place this dielectric medium inside the electric field. So you try to have two parallel plates, one connected to the positive terminal, the other connected to the negative terminal of the sources of EMF or battery. Okay, then what happens? Positive charge will be developed on one side, on the other side negative charges will be developed. So electric field will be there from positive plate to the negative plate. That means from in my diagram from left to right, and that electric field, before placing this dielectric medium here, let the medium between the two plates be vacuum or air. So we may denote that electric field by E naught vector, right, from positive to negative plate. Now what happens when dielectric medium is placed or inserted inside this parallel plate or inside this electric field? What happens? The dielectric atom now get polarized, two poles. So what happens? Positive will be there and those electrons will be shifted toward the positive plate. So what happens? Two poles are formed, okay, for each and every atoms inside the dielectric medium. So we call it this phenomenon as polarization. So as these negative charges are toward the positive plate, what happens? The dipole moment will be from where to where? From negative charge to positive charge. So this like this. So your negative charge is there, positive charge is here. So dipole moment will be from negative charge to positive charge like this. Okay, your dipole moment will be in the direction of the applied electric field. But what happened in this case, as these negative charges are on the left hand side and positive charges on the right hand side, so what happened? The two ends of these dielectric medium seems to be polarized. On this side negative charges will be developed, on the right hand side of the dielectric medium positive charges will be developed. That means just opposite to the adjoining plate, okay, which produces this external electric field. So what happened? Near this positive plate onto this dielectric medium negative charge will be developed, and near to this negative plate onto the dielectric medium, what happened? Positive charges will be developed. So there will be again another field due to this polarization, and it will be from positive charge and toward the negative charge end, and that electric field is denoted by EP, P for polarization. Okay, so the net electric field, okay, inside the dielectric medium will be the difference of these electric field E naught and EP, E naught being greater in magnitude than EP. So your resultant electric field E will be equal to what? E naught minus EP, E naught minus EP here like this. Got it? So what happened? The resultant electric field what decreases when this dielectric medium is inserted. So such phenomenon of forming two poles, or rather the two poles on the sides of the dielectric medium when placed inside the electric field, we call it that phenomenon as polarization of dielectrics, okay, when placed inside the electric field E. Now you know that, as I said, E naught is greater than EP, right? And what is meant by this dielectric constant? This dielectric constant is nothing but, you may define this in terms of ratio of electric field E naught to that of the reduced electric field E. So E naught divided by E will be known as what? Dielectric constant K, and it may be written as E naught divided by E is equal to the dielectric constant K. Got it here? So E naught divided by E, okay, E naught divided by E is equal to K. This is known as dielectric constant, and this dielectric constant, as E naught is greater than E, what happened? Your K will be always greater than 1. Don't forget, okay? Now let's see about the capacitor of the conductor or capacitor and its capacitance. Okay, So what is this capacity? Capacity of a conductor is related to its ability to store the electric charge. Okay, the more the electric charge is stored, we said that the capacity of the conductor is more. So the capacity of a conductor is related to its ability to store electric charge. You can say electric charge or electrical energy. Okay, electric energy you can say. So what happens when electric charge is stored? Then what happens? The energy that is stored will be in the form of electric field energy. So we may call that energy as electrical energy, right? Now it is found that, okay, it is found that, or it is observed that if this potential due to a single point charge, we know that it depends upon the amount of charge. Okay, the electric potential V due to a single point charge, we know that it is equal to 1 by 4 pi epsilon naught Q by R, right? So what happened? Your V is directly proportional to Q. The more the charge Q, your potential V, which is equal to 1 by 4 pi epsilon naught Q divided by R. You know that Q and V are directly proportional, right? So what happens when more charge is given, then potential is also more. So it has been observed that potential of a conductor is proportional to the charge on it, right? But while writing, we have to write it Q is directly proportional to V. Then what happened? Your Q is equal to CV. In order to change from proportionality to equality, we require a constant of proportionality, and that constant of proportionality here we denote it by C, and this C is known as what? Capacity or capacitance of that conductor. Okay, that conductor, if has the ability to store, then that conductor may be called as capacitor also, right? And this C, the capacitance or capacity of that conductor, depends upon the various factors, and it depends upon what? It depends upon the shape, whether that conductor is having spherical, then we may call it as spherical capacitor. If it is of cylindrical, then we may call it as cylindrical capacitor. If it that of a parallel plate, then we may call it as parallel plate capacitor. And it also depends upon the dimension, the size, the shape, the area, the volume. Okay, that we call it as dimension, length, breadth. Okay, so what happened? Depending upon its area, okay, depending upon its area, depending upon its distance between the two plates, you may have different value of capacitance, right? And the nature of the medium that is placed, okay, the nature of the medium that conductor or that capacitor is placed. So depending upon that, what happened, we may call it them as what? If the medium is dielectric, then we may call it as what? Parallel plate capacitor, okay, or dielectric medium in it. We may also call it as what? Your electrolytic capacitor if the intervening medium is what? An electrolyte. We may call it as paper capacitor or mica capacitor or ceramic capacitor, okay, depending upon the medium. Also dielectric medium also we may call them as differently, right? But it is independent of the material of the conductor, whether you are having a copper capacitor or iron capacitor or silver capacitor. It is immaterial, so it doesn't depend upon the material, the nature of the material of the conductor, right? It depends only on what shape, dimension, and the nature of the medium, right? Now let's try to express this. C is equal to Q by V. Now how to remember that? There is always a confusion. Okay, Q is equal to VC. In the examination, many students will have a confusion that C is equal to whether it is V by Q, like that. Okay, not Q by V. Q by V is the actual one, but you will want to write what? V by Q. So how to remember that one? I have one mnemonic. Okay, if you want it, then you can use it. Otherwise you can also find your own mnemonic. Mnemonic means something to help regain your memory, okay, that we call it as mnemonic. Now Q is equal to VC. If you remember this equation, then it will be very easy to express C is equal to Q by V, right? So now you know in university, in a university, what happened, there are many departments, right? Life science department, chemistry department, physics department, like that. Okay, many departments are there. So in that university, whole of the department, okay, the responsibility is on to that vice chancellor. He is responsible for whole of those charges of all those different departments. So the whole charge, what or responsibility lies on VC. You remember in that way. VC means, B means potential, C means capacitance. If you remember like that, then you will remember this equation and you will have no difficulty in expressing C. Okay, C will be equal to Q by V. So your capacitance of a capacitor may be defined as a ratio of the charge given to the conductor to its potential. Okay, so you may define that capacitance as what? Ratio of charge given to the conductor to its what? Potential. Now if V is equal to 1, that means if V is equal to unit quantity, then your C will be equal to Q, right? By 1 that is immaterial. So but at the time of giving the definition, that 1 is required, right? So what happened? Your C will be equal to Q. Thus the capacity of the capacitance of the conductor or capacitor can also be defined as a charge required to raise, okay, the capacitance of the capacitor may be defined as the amount of charge required to raise it through a unit potential. This is to be given there. The condition is what? The capacitance of the capacitor is nothing but this is the amount of charge required to raise, okay, required to raise that conductor through a unit potential. That we call it as what? Capacitance. Its SI unit is what? Farad. Yeah. Capacitance is measured in terms of farad in SI unit and it is denoted by capital F. So 1 farad will be equal to 1 coulomb by 1 volt. That is what I'm writing here. Okay, 1 farad will be equal to what? SI unit of charge is coulomb, SI unit of potential is volt. So 1 farad will be equal to what? 1 coulomb by 1 volt, right? So but this is a bigger unit. So there are smaller units which are practically used. So some of the smaller practical units are what? 1 microfarad, mu, 1 microfarad. Micro means what? 10 to the power minus 6. Nano means what? 10 to the power minus 9. Pico means what? 10 to the power minus 12. So 1 microfarad, 1 nanofarad, 1 picofarad. These are all the smaller practical units they are using in our day-to-day life, right? So these are the practical smaller units. And how to represent these capacitors symbolically? Okay, that means to write or to draw what your capacitor we can draw by using two parallel lines like this, whether it may be vertical like this or horizontal, doesn't matter. Okay, and there will be two connecting leads like this, and it is just somewhat similar to that of a cell, but it is not equal to that of the cell, because in the case of cell one line is longer than the other, right? But here what happened, the two lines will be of equal length, okay, parallel to each other, and with two connecting leads like this, this will represent the fixed capacitor. Fixed capacitor means the value of the capacitor or its capacitance is constant, that we call it as fixed capacitor. And this is a variable capacitor. Onto that fixed capacitor, if you draw one arrow on it, then it will represent what? It will represent variable capacitor. And in the case of electrolytic capacitor is what? Your electrolytic capacitor will be denoted by just like the fixed capacitor, but with one polarity, minus sign and positive sign will be there. In the case of the intervening medium of an electrolyte, that capacitor we will call it as electrolytic capacitor. And in that electrolytic capacitor, what happened? Polarity will be there, negative and positive. But in the fixed capacitor, there is no such polarity. You can connect it with one or the other, same. Okay, but in this you need to see the poles. Okay, which one is negative, which one is positive. You need to see these poles. Okay, so such type of capacitor which has the dielectric medium as an electrolyte, we call it that type of capacitor as electrolytic capacitor, and it has two poles, negative and positive, like this. Okay, now let's see about the capacity of an isolated spherical conductor. Now first we need to know that if this is a spherical capacitor, a spherical conductor of radius r and at center O. If Q charge is given onto it, we know that charge will reside on its surface, right? But if you want to find potential at any point on its surface, then the whole charge will be assumed to reside at its center, right? So we need to find out that V somewhere here, okay, onto its surface. Then charge Q divided by V, that will give you your capacitance, right? So we know that potential, electric potential due to this Q, which is assumed to be concentrated at the center at this point, okay, of distance r from it, the electric potential is what? 1 by 4 pi epsilon naught Q by r, right? We have learned this in the case of electric potential due to a single point charge, right? So if you divide that charge by its potential, then Q will cancel and you will get 1 by 4 pi epsilon naught times r. And we also know that at the time of Coulomb's law, that 1 by 4 pi epsilon naught, we generally take it this as electrostatic constant, and we found that we have learned that this 1 by 4 pi epsilon naught, this will be equal to 9 into 10 to the power 9 Newton meter square per Coulomb square, right? So this value, if you place it here, then instead of 1 by 4, then it will be 1 by 9 into 10 to the power 9, right? So 1 by 9 into 10 to the power times r, this will be the expression of your capacitance due to that spherical capacitor of radius r. So we know that your capacitance is directly proportional to its radius. Larger the radius of the spherical charged body, more charge can be accommodated or stored in it. Now when charge is given, what happens? That charge will have to be distributed uniformly, right? So if more spherical size of the conductor is large, that means more amount of charge can be stored or can be placed on it, right? Can be given to it, right? So what happened? Let's see what will be the radius of this capacitor, rather the size of the spherical conductor, when the capacitance is to be of 1 microfarad. So in order to have this 1 microfarad capacitance, let's try to find out how long the radius of this spherical conductor would be. Now if you put that 1 by 9 into 10 to the power 9 into r, then means what happened? R will be equal to 10 to the power minus 6. Why? Because we are going to have the capacitance as 1 microfarad. Okay, 1 micro here farad times 9 into 10 to the power 9. If you cross multiply it with that 1 microfarad and this 9 into 10 to the power 9, then you will get as radius. That is what I'm writing here. So it will be equal to what? 9 into 10 to the power 3 meter, right? So 9 into 10 to the power 3 meter means this is kilo. So kilometer, 9 kilometer. So in order to have this 1 microfarad capacitance, the size of the spherical conductor, its radius will be of 9 kilometer. Wow, it is huge, right? So it is a very large spherical conductor. Then what happened? So in this large spherical conductor, see, radius is 9 kilometers, so diameter will be of 18 kilometers. So it is a very huge spherical conductor. So but we don't want such a huge capacitor, because it is not efficient. Okay, we want to find out an arrangement so that what happen, large amount of charge can be stored in that small space. Got it? In that small space, if we can store a large amount of charge, then what happen, that will be much effective, right? So it should be AC is this will be space. Okay, you try to put that A and CE here. Okay, this is what space, in a small space. So in trying to find that device or arrangement which has a larger capacitance in a smaller space, we need to learn more about the other type of capacitor, what we call as parallel plate capacitor, and that will be done in our next class. For today, let's wind up here. Okay, let's meet in the next class, right? Okay, thank you.